Final Project for AP Calculus BC by Leslie Oy. Topic 1. Partial fractions. We can split the denominator through partial fraction decomposition. This is the process of breaking up a fraction to express it as the sum or difference of multiple fractions. Through partial fraction decomposition, we can then integrate partial fractions by using natural log integration rules. We need to do long division before decomposing a fraction when the numerator has the same or higher degree than the denominator. For AP Calculus BC, we will only decompose fractions when the denominator can be factored into non-repeating linear factors, so we won't work with repeated factors and/or quadratic factors. Here are the steps for partial fraction integration. First, factor the denominator of the original integrand. Then, rewrite the integral as a sum of multiple fractions, each having a denominator equal to a factor of the original function. Then, we will solve for the coefficients of each of the decomposed fractions, and we will rewrite the integral as separate integrals of fractions with linear denominators. Then we will factor out the coefficients of the integrands in front of the integral signs, and integrate each component using natural logarithms. And don't forget the constant of integration. Then we will finally use the properties of logs to combine the integral into one logarithm if necessary. A real-world application of partial fraction decomposition is the fact that we can find inverse Laplace transforms through this process. Here's a table with some examples of Laplace transformations. Laplace transformations are used in physics and engineering to analyze linear time invariant systems, such as electrical circuits, harmonic oscillators, optical devices, and mechanical systems. An example career that uses partial fraction decomposition are geologists. They use it for studying plate tectonics, which began around the mid-20th century. Geologists track elevations and contours of the land to study how recently the Earth's motions impacted mountains, valleys, and other landforms. Eventually, they can plot the elevations on a chart that basically gives a cross-section of the area they're studying. Geologists can then integrate the curve to find the hyposymmetric integral for the region and then create mathematical models for how an area's features has changed over time. So, as shown, through partial fraction decomposition, geologists can analyze the movement of the Earth's crust even though it moves extremely slow. Let's move on to a different topic. Vector-valued functions. These are functions with the domain subset of real numbers while the range is a set of vectors. This can be denoted as the following, or through using unit vectors like this. There are three vector types that we can use to describe particle motion. There's the position vector, the velocity vector, which has x prime of t that describes the velocity of the particle in the horizontal direction, or the rate at which the x-coordinate changes with respect to time, and y prime of t, which is the rate at which the y-coordinate is changing with respect to t, or the velocity of the particle in the vertical direction, and then finally the acceleration vector at any time t. We can also calculate the second derivative with respect to x. If the smooth curve C is given by the equations x equals f of t and y equals g of t, then the slope of the C at the point xy is given by the following. We have dy dx equals dy dt over dx dt, where dx dt is not equal to 0. This is the slope of the tangent line, the slope of the path of the particle traveling along the curve C, as well as the rate of change of y with respect to x, and then we find this second derivative by the following. And this is essentially the rate of change of the slope of the curve C with respect to x. So how do we calculate this? First we have to calculate dy dt, then divide this value by dx dt, provided that dx dt does not equal 0, and then calculate the derivative of dy dx with respect to t, and then divide again by dx dt, provided that dx dt does not equal 0. Here are two formulas that are helpful for particle motion as well. The The first formula is the speed of the particle, or the magnitude length of the velocity vector. The second formula is the length of the arc of the curve from t equals a to t equals b, or the distance traveled by the particle from t equals a to t equals b. So you might be thinking, how does this connect to parametric equations? Well, they're very similar, except mainly for the fact we would have vectors instead of points on a graph. Here's how that's illustrated below. A real-world application of vector-valued functions is, remember, that air currents reflect both the wind speed and wind direction. So physicists can model these currents with vector-valued functions which reveal the air current's direction and speed. Through understanding these vector-valued functions, meteorologists then can predict the weather in a certain area, whether it be cloudy, sunny, or stormy. A career that utilizes vector-valued functions are robotics engineers, who work with material scientists to control the robot building process. Engineering teams will use vector-valued functions to define the rate at which the robotic parts can rearrange themselves. Using vector-valued functions to express rates of change is advantageous because it allows researchers to quickly find the sum of the changes in the new form or position of the robot.